Alright, today we're going to be looking at the Physics Paper 6 Alternative to Practical paper. There we go. That's from May-June 2016. The paper code is 0625/61 and this is the Cambridge International Examination. Alright.
Are you ready to begin?
Question number 1. A student is determining the weight of a meter rule using a balancing method. The apparatus is shown in figure 1.1. And here we go, let's run through what the student does. We can see it's an interesting little method there. They've got some kind of a meter rule and they're just balancing it with a couple of weights on either side and a pivot somewhere in the middle there. There we go. Alright, the student places the load P on the meter rule at the 5 centimeter mark. She places the meter rule on the pivot at the 45 centimeter mark. Okay, so we got a load, we got 45 centimeters. She places load Q on rule and adjusts its position so the meter rule is as near as possible to being balanced. She measures the distance x from the center of the load P and the pivot and the distance y from the center of the load Q to the pivot. She repeats the procedure, placing P at the 10, 15 and 20 centimeter mark, and the 25 centimeter mark. The readings are shown in table 1.1. Let's have a quick look at that. There we go, bunch of readings. Makes sense. 1. For each value of x, calculate A equals px, where P is 1 Newton. Record the values in the table. P is the weight of load P. Now, P is on the left at the 5 centimeter mark. Oh, let's just find out which one's which. So this is 45 centimeter mark. This is 40 centimeters in between there and there for that first one. And there we go. So P is x. She measures the distance x from the center of load P. We have to calculate A equals P times x, and P is 1 Newton. So A equals Px. So 1.0 newtons times x. Well, 1 times any of those values x is going to give us the same number. So 40.0, 35.0, 30.0, 25.0, and 20.0. Nice easy start, good. And now for the final one, B. B equals Qy, where Q is 0.8 newtons. So 0.8 times 42.5, 0.8 times 36, and so on. And the next bit down the bottom, part 2, complete the column headings. Ooh, interesting. Well, we already know x and y are centimeters because it gives us that in the question. Centimeters, centimeters. Now if I multiply newtons by centimeters, newtons times centimeters, what do I get? Well, we don't get anything amazing or deep and meaningful. What we get is newtons, centimeters, newtons times centimeters. That's all that means. So let's write that in. Newton centimeters, Newton centimeters. There we go. That bit's done. B. Plot a graph of A in Newton centimeters and the y-axis against B in Newton centimeters on the x-axis. Start both x's at the origin 0, 0. Ah, key point here. That's actually very important. Why is that very important? Well, because normally when you've got this sort of large gap, as we have in the tables, what you would be likely tempted to do is put an asymptote, a little jump in the axis. But here it's telling us very clearly start both axes from 0, 0. So we avoid what we would normally do and we follow the instructions that are given to us because there's guaranteed to be a mark for that. The first thing we do, of course, just draw in our axis lines. And we label our axes. A in Newton centimeters and B in Newton centimeters. Interesting point, of course, here is these units. It's giving us the units here. It asked us to write units in our table. If we weren't sure what the units were at this point, the question's already given it to us. We could go back and just either check our answers or put in answers to make sure we get the marks. Now, we want to go up to 40, so from 0, 0 to 40 on, or from 0 to 40 on the y-axis, so 10, 20, 30, 40. And from 14 to 34 on the x-axis, so 10, 20, 30, 40. That's the best axis scale to use. And now we go in and we start marking our points on the graph. So 40, 34, and we just keep marking the points in. And there we go, that's the points now marked on the graph. Let's see the next section. Using the graph, determine the vertical intercept y. Show clearly on the graph how you obtained this value. Alright, so we're going to do a line of best fit and continue it till it hits the y-axis. Okay, and that will show on the graph clearly how we got the value. And there we go, that's our line of best fit. I mean, now's a good time to look at your line, look at the points that you've used and make sure that they're all where they need to be. And what I can see is that one of my points is very slightly out from where it should be. So all these things that you're doing as you run through it gives you a chance to check what you've already done to make sure that you've got it right. Now, I want to find a point where it intercepts with the y-axis, the vertical intercept. And that happens just there, which is at 6 is the value. I'm just going to label that as an intercept. Now it's very clear on the graph what's happened. Now, if you look closely, you'll see I've made a mistake. Centimeters, Newton's centimeters. There we go. Calculate the weight W of the meter rule using the equation W equals Y over Z, where Z is 5 centimeters. So that tells me that W equals 6 Newton centimeters divided by 5 centimeters, which gives me 1.2 newtons. There we go. And suggest one practical reason why it's difficult to obtain exact results with this experiment. The balancing of these little meter rules is an absolute pain. So, difficult to balance. There we go. Right, part F. The student uses an accurate electronic balance to obtain a second value for the weight of the meter rule. And it gets 1.24 newtons. State and explain whether the two values for the weight agree within the limits of experimental accuracy. Oh, interesting question. Why is this an interesting question? Well, because a lot of times when they ask this question, you would just say it agrees within the limits of experimental accuracy. But here, because they've stated that in the question, they've taken that out of your answer. You can't just write that. You can write something similar, but you can't just use that kind of stock phrase, if you like. Okay, so statement, well, I'm going to say yes, these agree. Yes, these values agree. And the justification, well, the values are close enough together to say they agree. There we are. Next one. Question 2. A student is heating water in a beaker using an electrical heater. He measures the potential difference V across the heater and the current I in the heater. Write down the readings shown on the meters. Ooh, okay. If I'm looking here, that looks like about 8.1 to me. And this is 0.5 there. So 0.45. So let's write that down. We've got 8.1 and 0.45. Key points. There's no units, so we have to make sure we write them in. V, volts are measured, voltage measured in volts, potential difference measured in volts, and current is measured in amps. Always make sure you check the units. He measures the temperature of the water before heating. Write down the temperature reading theta shown in figure 2.2. Well, that looks like about 19 to me. 19, again, no units, degrees Celsius. In fact, it's written up there, always good to double check. Part C, on figure 2.3, draw a line and an eye to show clearly the line of sight required to read the volume of water in the measuring cylinder. So it's a question really about where you put your eye. and you want to put your eye at 90 degrees. There you go, beautiful. 90 degrees to the level of the water in the measuring cylinder. And make sure it's not at the top of the meniscus but flat with the level in the middle. Question 3. A student is investigating the resistance of a lamp filament. The circuit is shown in figure 3.1. Okay, so we've got a resistance wire, we've got a lamp, voltmeter across the wire, and it looks like a sliding contact with an ammeter attached to it. The student places a sliding contact C on the resistance wire, a distance of 0.2 meters from point A. He measures the current I in the circuit and the PD V, potential difference volt V, across lamp L. He repeats the procedure using values for D of 0.4 meters, 0.6 meters, 0.8 meters, and the readings are shown in table 3.1. Calculate the resistance R of the lamp filament for each set of readings. Use the equations R equals V divided by I. There we go. So it wants us to use the equation R equals V over I. We've been given V, we've been given I, so we're just dividing one by the other. So the first reading will be 1.6 divided by 1. And we just run through that for that column. Now what I'm going to do with this is just run through. I'm going to want to alter the same number of significant figures. I'm going to choose 2. I think 2 is a good number because some of them have just got one significant figure, some of them have got 3, well, one of them's got 3 but only 1. So I think 2 significant figures is a good number for that. Alright, so now part 2, complete the column headings in the table. Well, D, we're told that the distance is measured in meters, we're given that. V is voltage, it's measured in volts. I is current, it's measured in amps. And R is resistance, it's measured in ohms. Part B, the student notices that the lamp does not glow when he takes the final set of readings. He thinks the filament has broken. State whether the student is correct and give a reason for your answer. Has the circuit broken? Has this lamp broken for the final reading? Looking at that, I'm going to say no. Why am I going to say no? Because of this. There's a current travelling through the circuit. If the lamp was broken, there would be no connection, there would be no current. So statement, no, the lamp is working. And the reason? There is a value for the current. C. A student suggests that the resistance R of the lamp filament should be constant. Suggest, referring to the observations, a reason why the resistance R may not be constant in this experiment. Okay, let's look at those readings. What we see here, there we go. We can see it starts off, it doesn't glow at all. And it ends up at the other end of the spectrum very bright. Now, as it's happening, what we see is the resistance is getting larger as the bulb is getting brighter and as the current is increasing. So resistance is increasing as current increases and the brightness is also increasing. So what's happening to the bulb to mean that the resistance is changing? Well, the temperature of the wire in the bulb is getting hotter, and an increase in temperature means an increase in resistance for everything except a thermistor. So let's answer the question. As the current increases, the temperature of the bulb increases. The brightness also increases and the resistance increases. So really our key points here is that the resistance is increasing and the temperature of the bulb is increasing with the current. Those points. D1. Name an electrical component that could be used instead of the resistance wire AB and sliding contact to vary the current I. Well, what they're actually doing with that sliding current is they're varying the resistance of the circuit. And we can do that much easier with a variable resistor. Draw a diagram of the circuit including this component instead of the resistance wire and the sliding contact. Okay, so for that one, let's do a little power supply here. Circuit runs down here, runs over to our bulb, and make sure that the wires all meet. There can be no gaps whatsoever. You put in gaps, you'll lose marks. Doesn't matter if you've got it right, you'll lose marks. So make sure all the wires are attached and join on. There we go. So our main circuit, and what we're going to do is put in our variable resistor. And now one little ammeter, and we're done. Perfect. Question 4. A student is investigating the effects of insulation on the rate of cooling of hot water in a 250 centimeter cubed container. The student can choose from the following apparatus: thermometer, glass beaker, plastic beaker, copper can, measuring cylinder, 3 different insulation materials, clamp, boss and stand, and stopwatch. Okay. Plan an experiment to investigate the effectiveness of the 3 insulating materials. You should explain briefly how you would carry out the investigation. State the key variables you would control. Draw a table or tables with column headings to show how you would display your readings. You are not required to enter any readings in the table. And finally, explain how you would use your readings to reach a conclusion. A diagram is not required, but you may draw a diagram if it helps your explanation. Okay, so we're going to start drawing a diagram. First of all, what we're actually doing here is investigating the effectiveness of 3 insulating materials. We've been given a variety of different containers: glass beaker, plastic beaker, copper can. I'm going to use the copper can, but I'm only going to use one. I'm not going to use a plastic beaker and a glass beaker as well, because I have to control something. The thing that should be changing, in fact, the only thing that should really be changing in terms of when I'm repeating the experiments, is the insulating materials. I'd want one as a control with no insulating materials, and then try each of the 3 insulating materials separately. But I'd want to keep using the same container. It doesn't matter which one I'm using, but I have to keep using the same one. So here I'm going to use a copper can because, well, why not? And of course we've got clamp, boss and stand. We've got a thermometer. We've got the copper can. Let's start setting things up. There we go, 1 copper can. It's not beautiful, doesn't have to be. Inside my copper can is going to be the world's most awesomely drawn thermometer. There we go. Alright. And then my little clamp and boss. Doesn't have to be exact, doesn't have to be perfect. I'm not trying to win some kind of award here. Just has to be reasonably good. And I'm just going to straighten this up. Just I guess because I can. If you're running short on time, don't worry about straightening it up. Okay, and as this is my little drawing from what I'm going to do, I'm going to cover everything here in insulation. And I'm going to label it all up. Insulation, copper can, water, thermometer, clamp and boss. And there we go. That's the setup I'm going to use. Let's work through it. So the other thing I'm going to need to control, of course, is the amount of water that goes in. So let's begin with that. We're going to do a run through of what I would expect to do every time I do the experiment. So the first one I'll do, of course, would be the control. I want to measure 200 millilitres of hot water and place it in the copper can. I want to put the thermometer into the water and hold it with the clamp stand and boss. There we go, the first two steps. So I put the water in, I'm now holding the thermometer in place. What I want to do next is, once it reaches a certain temperature, start the stopwatch. So once the temperature reaches 70 degrees, start the stopwatch. And I'm going to want it to run for a solid 5 minutes every time. So stop it after 5 minutes and take the final temperature reading. And of course this is the control. Control trial with no insulation. Then I want to repeat the above process 3 times using the 3 different types of insulation. I'm going to want to record the results that I've got in the table. So let's put out a table for it. Right, so what am I going to record? Well, first of all, the material, then the start temperature, the stop temperature, and the change in temperature. So let's just write down the materials we'd be expecting to use. There we go, so we've got none, we've got the control attempt, and then we've got material 1, material 2, material 3. We're just writing that down because they haven't told us what they are. And that's fine. Okay, now the way we would then examine the materials for their insulating properties is compare the change in temperature that occurs. The most effective insulator would be the one with the smallest change in temperature. So compare the change in temperature for the different materials, and the most effective insulator would have the smallest change in temperature. Let's just write down some of the things we're controlling. We're going to control the type of container we're using, the start temperature, the volume of water, the time that we're measuring for. And there we go. All done. Good job. Right. Let's jump on to question 5. Question 5. A student determines the focal length of a lens. The apparatus is shown in figure 5.1. The student places the lens a distance u from the illuminated object. He moves the screen until a sharply focused image of the object is seen on the screen. On figure 5.1, measure the distance u from the illuminated object to the centre of the lens. Okay, that's using your ruler. And the same for the next bit, measure the distance v. So both of those are going to be using your ruler. If you've printed this off and you're doing this at home or you're doing this in the lesson, the result that you get will not be the result in the mark scheme because it'll be out by a millimetre or 2. And that's because you printed it and it's shrunk it or changed the size to fit specifically onto the paper you're printing on. Now, when I measured it, I got 47 millimetres, and that's because it was being printed onto letter size paper. So the way it resized it, it gave me 47 millimetres for U. The answer in the back is 50 millimetres. Equally, when I measured V, I got 19 millimetres. The answer in the back is 21 millimetres. So be aware, if you're practicing this at home or you're practicing this in the school and someone has printed it out onto normal size paper, then it will come out as a different answer. Don't worry about that. Okay, so the numbers they're looking for here are 50 millimetres and 21 millimetres. There we go. B, figure 5.1 is drawn 1/10 of the actual size. Calculate the actual distance u from the illuminated object to the centre of the lens. Okay, well, if it's 1/10 the size, it'll be 10 times bigger, 500 millimetres. And the same with V. V will be 210 millimetres. And calculate the focal length by using that equation, uv divided by u plus v. Okay, so that's 500 times 210 divided by 500 plus 210. And that gives us a value of 148. However, if we look at it, we can see that 3 significant figures is probably a bit too many. I think 2 significant figures is much more appropriate. And that gives us 150 millimetres. C. A second student repeats the experiment 3 times using a different lens. His value for the focal length of his lens are shown below. His values are shown below in table 5.1. Calculate the average value F2 for the focal length of this student's lens. Okay, we get 3 readings. We want the average, so that's just going to be the mean. Let's add them together and divide by 3. So that gives us 136 millimeters. Part D. A third student using the same method finds that the focal length f of her lens is 200 millimeters. She reads in a book that when u equals 2f, the distances u and v are equal. Okay, we've been given the value for f and we're asked to calculate 2f. So that's 2 times 200 millimeters, that's 400 millimeters. And as we come down, the student sets up the apparatus as shown in figure 5.2. She adjusts both x and y to be 400 millimeters. She observes that the image is blurred. The student slowly increases the distance y and obtains a sharply focused image when y is 406 millimeters. Discuss whether the student's results confirm the statement in the book. Well, to my thinking, that's pretty close to 400. It's only 6 millimeters out. So I would say that yes, the statement is correct, and I would say within the limits of experimental accuracy. That one stock statement that we couldn't use earlier on. We can certainly use it now, and I think we should. Part E suggests 2 precautions you would take in this investigation in order to obtain reliable results. Well, step 1, whenever you're doing any of these focusing experiments, you need a dark room. If it's not a darkened room, then you're going to struggle to get any meaningful results. So that's 1. And number 2, the other thing that's difficult is to find or to measure from the center point of the lens. But what you can do is you can mark the center point of the lens on the lens holder. And that gets rid of 2 of your biggest problems. So there we go. Use a darkened room and mark the position of the center of the lens on the lens holder. Now, both those points will make it much easier. Alright, hopefully you found that helpful. Please feel free to like and subscribe if you enjoyed it, if you've got any papers that you'd like me to cover. And of course, not just limited to the CIE syllabus, but if there's anything else you'd like me to go through, just leave a message in the comments below. And you know what? Have a great day.